Okay, here's the circuits lab for PHYS 2212. To begin, our mission here is to basically prove that charge energy and conservation in a DC circuit exists, as well as to find the time constant and approximate it in an RC circuit as well. Our models and principles here include Kirchhoff's loop rule, current conservation, as well as ohmic resistors and capacitors. What will happen is basically the voltage differences from the voltmeter will satisfy the loop rule, and linearization will allow us to estimate the RC value very accurately as well. Our ideas here for physics include Ohm's law, which allows us to find the current given voltage and resistance, where V equals I times R, therefore I equals V divided by R as well. Total resistance in a series circuit is where R total equals the sum of the R1, R2, Rn, etc. within the entire circuit. The time constant is when the voltage difference of a circuit has dropped to just 1 over E of its original value, represented as tau equals R times C, where R is resistance and C is capacitance. Node rule is when current flowing into the node equals current flowing out of the node, and loop rule is when voltage potential difference around the loop is just 0 in total. For the experiment details, the system is the circuit and the ammeter and voltmeter. Everything else in the surroundings besides that. I use the Colorado FET circuits construction kit to simulate the DC circuits and then RC circuits as well. For DC, I correctly found the current in the circuit to be 0.02 amperes based on Ohm's law, knowing it's constant throughout the entire series circuit. I summed the series resistor to simplify the circuit as one giant resistor only in that case to make it easier to work with and analyze. And also I graphed the voltage potential as part of the circuit using the voltmeter and verified using the loop rule. I see that in this case the end voltage equals 0 because after the entire loop is over, the sum of all the voltage differences equals 0 at the very end, satisfying Kirchhoff's loop rule. And the voltmeter did not affect the current measurement because voltmeters have very high resistance. They don't actually take up very much current at all within the ammeter, so it doesn't affect the ammeter's readings very much at all. However, when I put another ammeter parallel to the 100 ohms resistor, it changed the current because it could easily bypass the resistor and make it messed up in that sense, as shown in this image here. And also part 3 of this, next part is the RC circuit, where I basically just measured time to both charge and discharge a 0.2 farad capacitor. Then I applied energy and conservation to a simple RC circuit to get delta V capacitor plus delta V resistor equals 0 in total. By rewriting the voltage potentials and solving some differential equations, I got delta V equals delta V not exponential to the power of negative T divided by RC, and log it to both sides to get ln of delta V equals ln delta V naught minus T divided by RC. And here's the circuit for the RC capacitor and resistor circuit. To find RC, I first simplified to get this equation, to linearize it, and plot it in the spreadsheet here to get the following graph, and got this, where the slope of the line is therefore negative 0.165, and I set it's equal to negative 1 divided by RC, and solve for RC equals 6.06 seconds, which I found the actual RC to be value to be 30.0 ohms times 0.20 farads equals 6 seconds in total. Therefore, my estimate is very close to the actual value of the RC value, with a error of 1% in total, which is very low, I feel like, and therefore very effective with this almost perfectly correlated and very straight line trend line here. And error sources include, we assume that the wires were perfect and all had zero resistance, although this could be far from the truth. There's delay between pausing the stopwatch and actually discharging the capacitor because of human error. And the online circuit simulations do not accurately portray all aspects of real-life circuits as well, causing some inaccuracies there. As for what if and what does it mean questions, what if I had used an actual ammeter instead of an ideal simulated ammeter? In that case, real ammeters have non-zero resistance and therefore cause a noticeable voltage drop within that resistor's path in that current. What if I were to use a real battery to charge a real capacitor without a resistor at all? The simulation showed in the capacitor instantly charging up the battery even caused a small fire in that case, but it would be slower in reality because resistance from the battery as well as the wires block the current from immediately reaching the capacitor, therefore causing a more abrupt delay and therefore making it much slower to get to the stage of being fully charged in the capacitor's case. To conclude the video here, while ammeters and voltmeters are real components of a circuit, their effects on measured current and voltage from ammeters and voltmeters tends to be very minimal and small and trivial in that case. All aspects of a series circuit can be easily calculated using Ohm's law and other properties too, such as Kirchhoff's loop rule, as well as the node rule, as well as even the resistors in series and parallel rules as well. And circuits are pretty darn cool in conclusion, and therefore very interesting in applications like, circuits and robotics, or things like infrastructure, power grids, etc. So it's a very cool field to explore. I hope you enjoy the video, and that's about it for me. Uh, that's all, folks. Goodbye.